This is all about how the seasons change and why, and it has everything to do with solar energy and how it's received by the surface of the Earth. And for starters, let's have a look at the big picture, and you can see the various planets illustrated here. Some of the closer ones, and the Earth orbits once every year, and it comes close to the Earth during, it's funny, isn't it, January 3rd. So that must not be why it's colder up here, right? And it's at this point in history farthest away, July 4th. So kind of interesting dates. And so this relationship then between the Earth and the Sun is shaped by a lot of things. And what we're going to focus on, though, in this particular unit isn't so much distance from the Sun, though that varies some. And that does matter a little bit in temperatures. But the tilt of the Earth, how that influences all of that. So the Earth's orbit then, as we said, closest to the Sun, January 3rd, farthest July 4th. And so that's a fun one to share with your friends on July 4th, right? So what's the significance of today? Today we're farthest from the Sun. A lot of people won't believe you. They'll say, well, why is it so warm in July then? So that's another question, isn't it? So you should be able to answer that question when we're done here. So the Earth's energy budget then is shaped by incoming solar radiation and radiation leaving Earth from a warmed Earth by that solar radiation. And so there's a balance between inputs and outputs. And when that's in equilibrium, we don't get a change. Of course, it's changing all the time in a particular latitude, as we'll see in a moment. And that's why we have the seasons. So the electromagnetic spectrum is descriptive of the sun's radiation in the various wavelengths. It peaks, though, in the shorter ones in the visible light area, and that radiates long-wave infrared energy out at much lower energy. And just keep in mind that all substances emit radiation. The higher the temperature, the shorter the wavelength. Your body and the Earth emit long-wave radiation, and this hotter sun emits shortwave radiation. Now, sometimes we call long-wave radiation, we call it infrared, okay? So same concept there. I'm being a little bit redundant, but we will use both these terms. They're often used, both of them, in studies of this nature. Okay, so this is a picture graphically of that distribution, and you can see again visible spectrum is where we have a peak in terms of total energy, and the longer wavelengths, less and less. And so there's basically almost no overlap between, though that part of it, say between 5 and 10 micrometers, where the Earth's emission to outer space and the solar radiation coming in overlap. So the distribution of insolation, just keep in mind that the tropics receive more concentration or concentrated insolation, and in fact, because of that, they received about 2.5 times more incoming solar radiation than the poles. So insolation just means incoming solar radiation, okay? So this is kind of strange because the total hours of daylight per year are the same everywhere on Earth, okay? It's just that in the tropics, the sun comes in much more intensely at the surface. One little point on this that's kind of fun to think about, though, is that in June, which is the time of our longest days, more radiation falls per square meter in a day on the top of the atmosphere in latitudes like Vancouver, British Columbia, than in tropical areas, okay? And it's interesting here in the Willamette Valley, the months of July and August, we actually get more solar radiation here than Tucson, Arizona does. The days are a little longer, and they get a kind of monsoonal moisture that time of year in the southwest, and we tend to be at our very driest then. We do get some clouds, but thought you might find that interesting. It's true in Vancouver, British Columbia as well. All right, so I did another YouTube on this one. We'll skip past that, and that's part of your collection here. Seasonality then. Seasonality is caused by changes in intensity and duration of incoming solar radiation. The key related concepts is that the solar altitude is the angle above the horizon, which affects intensity at ground level. So when the sun is very high in the sky, like in the middle of the day in the early summer or late spring, that's a high solar altitude, can be almost 70 degrees here in the Willamette Valley. And the day length is another part of that, and that's also the time of year when the days are longer. So you have solar altitude, day length, and then driving this really is directly is where the subsolar point is on the globe, okay, in degrees of latitude, okay? So the declination or the latitude of the subsolar point, that's where the sun is directly overhead at solar noon. Okay, a little bit, there's a revolution of the Earth around the sun, and then there's Earth's rotation as well. Those are easy words to confuse. Just a quick note on that. So the reasons for the seasons then, I'm going to pause this for a moment. Okay, so the reasons for the seasons, really the key here is that variations in the duration and intensity of solar radiation received drive the annual march of the seasons, okay? So somebody says, why do the seasons change? I remember when I was a kid, I used to wonder, why is it that winter always comes every year? And I didn't really like the cold that much. I grew up far north of here, and I remember just hoping some year that winter wouldn't really come when I was really, really young. Well, that never happened. It was inevitable. And what happened is the days would get shorter in the winter, and the intensity of the solar radiation above the ground would be less. And that's really what's going on there. But why does that happen? Okay. So the tilt of the Earth's axis is a part of this story, and it's tilted at 23.5 degrees from the plane of the ecliptic, which you'll see in a media video here in a bit. And then there's also axial parallelism, where the axis maintains its alignment during the orbit around the sun. And you can have a peek at this now. This will be a nice little video for you to watch, and this is all available in the notes. So I'm not going to watch it here with you, but other than just give a very quick look at the very first part, just to give you a sense of how this works. See how it changes at these different spots. I just wanted to quickly show you that, okay? So it makes its trip around the sun, and at every particular point along the way, there is a particular Earth-Sun relation at any latitude. And so this would be the June solstice, the 22nd of June, and so on, all the way around. And so just watch this a couple times over. It'll really, really help you. I can go over and over this, but it's really a good video. And so definitely important in understanding the material if you want to do well. Okay, so there's that. And then I'll go back now to the PowerPoint. And we'll get back to where we were. So in doing this, that North Pole points toward the North Star, or Polaris as it's called, and thus the subsolar point or declination will vary in location between the tropic lines. And so as you watch that, you'll see how that happens. Like when we're in June, we're very much tipped toward the sun, and in July as well, but especially June 22nd is the peak of that. And then in the cold time of year, the northern hemisphere is tipped away from the sun. Okay, so again, recommend if you have trouble with this one, use this one. They're both in the notes there, so either way you should be good. Okay. So now I'm not going to have you like write all this down. It's in the notes, but just know this. Okay, I definitely have questions on this every time we have a test on this subject, so make sure that you understand this. From the period March 21st to September 21st, so if you're in that period, the subsolar point, or the place where the sun is directly overhead, is in the northern hemisphere. Okay, so if it's spring right now, and most of you are listening to this, probably spring term. Some of you will be fall and winter as well. But in that time of year, really spring and into the end of summer, into September, the subsolar point is in the northern hemisphere. In other words, the place where the sun is directly overhead is in the northern hemisphere, not the southern. It's north of the equator. Okay, so the day length is longer the farther north you go. For all places north of the Tropic of Cancer, solar altitude is highest on June 21st. Okay, so at the opposite time of year, everything just switches. Okay, so the sun is directly overhead in the southern hemisphere. That's what we call the solar declination. Okay, and so during that time of year, the farther you go south, the day length gets longer. Okay, or the farther north you go, in other words, the days get shorter. So when you're in that time of year, say around New Year's, is in that spell. If you were to travel anywhere north, the farther north you go, the shorter the days get. The farther south you go, the longer they get. Period. Anywhere in the world. Okay, we're kind of a handy generalization. All right. So then, just to kind of follow up on that, yes, the declination would be in the what hemisphere in that time period, and that's something you can pick up from the video. All right. So axial tilt and parallelism. Okay. So when we said plane of the ecliptic earlier, the idea is this kind of imaginary plane as the Earth goes around its sun in its revolution around the sun. It's always aligned on that plane of the ecliptic, but tip relative to the sun is different. Okay, and that's what that's about. But it's easier to visualize in the video than in a diagram like that, in my opinion. Okay, so what's the annual march of the seasons? Okay, so winter solstice, the subsolar point is at the Tropic of Capricorn. That's something you should commit to memory. So basically, this chart you should be able to commit to memory, and maybe the easiest way to do it is to think of it in this kind of trip here, maybe, or you could just see the progression there. Starting the winter, it's the subsolar point is at the Tropic of Capricorn in the southern hemisphere. Then it goes to the equator on March and June. It's directly over to the Tropic of Cancer, not that far from here, 23.5 north. And in the fall equinox, it's back to 23.5 degrees. Excuse me. In the fall equinox, which is September 22nd, the subsolar point is at the equator. And of course, it's heading south. Okay, so by the time you get to December again, it will be directly overhead at the Tropic of Capricorn. So we're back up to here again. Okay, so using a globe to sort of draw that out is maybe one good way to learn it. All right. So solar altitude then is the angle in degrees above the horizon, and the variations in solar altitude and day length drive seasonality. Okay, so when we say solar altitude, we just mean how high the sun is in the sky. So if you're here, the observer, and you see the sun there, that's about 30 degrees. Okay, if it's roughly halfway from horizontal, it'd be 45. It'd be up here somewhere. If it's 90 degrees straight up, you're in the tropics, that's for sure, and you're looking straight up at the sun, or it's shining down on top of you, on the top of your head. And so to calculate solar altitude, you just take 90 degrees minus the number of degrees of latitude that separate place of interest from the declination or subsolar point. Okay, and that can be determined by for the solstices and the equinoxes using the data already provided, shown here again. So this is a nice little box here that just sort of summarizes all that. If you know those points, you can then on those days say, okay, I know where the subsolar point is, or the declination as it were, and from that then I can calculate what the solar altitude is for people anywhere else in the world at any other latitude. That's the basic idea. Okay, and so then this is an example of that. Okay, and then here there's a video linked on this as well, how to do that. Okay, and so when you're in the notes section of this, just go ahead and click on that, and you can see that video. Okay. So this is kind of, you look at this and as another example, just to help you practice. Okay. So what ends up happening then is, depending on what time of the year it is, the observer would see the sun very high in the sky in the middle of the day in June, and not so high on these other times of the year. That's the basic idea, and that gives us solar altitude.